right, class, we're moving into a new topic, and it is going to be weathering and erosion. This is chapter 5 in our online textbook. And what we're going to do here is we're going to move away from surface fluids, water and ice, and even gas in our climate, and we're going to move into the rock cycle. So we could even just maybe say, let's say we're moving into the rock cycle. Into rock cycle. And the rock cycle is the birth, the change, and the destruction of rocks. And what we're going to do first is destroy them. All right, so let's destroy, and we're going to destroy by this process of weathering and erosion. We got two background concepts I want to work on, and you could say background concepts. Number one, nature acts towards equilibrium. Nature acts towards equilibrium. This is always true, but it manifests itself in different ways. With respect to earth and topography, what's happening here? Here we go. There's our landscape, and there's a cliff, and we have a house built on the bottom of the cliff. And let's say we have a big boulder right up here. Nature acts towards equilibrium. Equilibrium is flat topography. All topography, any mountain, any valley, that's metastability. Metastability is a temporary thing. So metastable equals temporary. But we are short-lived creatures. And so sometimes things that we think are permanent are actually temporary. For example, the person builds a house at the bottom of the hill. This boulder wants to crush that house. But it's held up at the top of this cliff by a metastable thing, and it's this lip. It can't roll uphill, so we need to erode this lip away before gravity will allow this boulder to reach its equilibrium, which is down at the house. This is how landslides work. This is how particles move. It's how water flows, of course, as well. I guess this is number two. Our background concept is water is driving force. To a large extent, water is the number one. Now, our caveat here is that both ice and wind are going to be fluids that are also going to be driving weathering and erosion, but to a lesser extent. So I want you to think that water is our driving force for both mechanical weathering and erosion and chemical. Water is the driver. All right, so there's our background. Let's get into some definitions here now. We're going to define weathering, and we're going to define sediment. Weathering is defined as processes that break up rocks. Break up rocks. It can be as simple as that. You can make it more complicated if you want to. Weathering is going to occur in two ways. It's either going to occur by chemically breaking up a rock or mechanically breaking up a rock, and we're going to get into those here soon. Now, when you break up a rock, you break it into sediment, which are the pieces of a rock, smaller pieces of a rock. And we'll define this as loose, disaggregated, that just means broken particles of rock. And I'm going to use the word disaggregated. If you don't know what that word means, you could just write the word broken underneath it. Loose, disaggregated particles of rock. And later we're going to teach you how we describe those particles by their size and their shape, etc. And what sediments do is they make up a surface veneer across our planet. Everywhere we look, for the most part, we see sediment covering the actual bedrock. So we have these two different topics within weathering, and they're mechanical and chemical. And what I would like to do today is I would like to just walk you through the types of chemical weathering. So we could have a heading here, and that heading is going to be chemical weathering. These are chemical reactions. And there's three of them that I want you to know. So we're going to go chemical weathering as a big heading. Underneath this, I want you to say this is reactions. These are reactions that dissolve rock. They alter rocks. And importantly, it's the minerals themselves. Let's see about this. Reactions that alter minerals. And minerals are the building blocks of rocks. So it's going to be of minerals, and some minerals are reactive, and some minerals are very stable. And we can't learn all those right now, but some of that I'll be teaching as we go through here. And then the next thing is that climate matters. For chemical weathering, climate matters. When you have a climate that is both hot and wet, with abundant water, then there's going to be an opportunity for chemical weathering. Cold, dry climates don't have as much chemical weathering. We have 3 types, 1, 2, and 3, and then this lecture is going to be over. First off is dissolution. And dissolution means dissolve. Within dissolving, they're going to all be, well, the first 2 are driven by water. So with dissolution, water is attacking the mineral. It's going to break apart the mineral, and it's going to release the cation. Releases cation, right? Cation is an element with a positive charge. So, for example, we could have a mineral calcite, CaCO3, and we add water to that calcite. We could have a mineral halite, NaCl, table salt, plus water. You know what salt plus water does. It dissolves. It releases the sodium as an ion, and it stays dissolved in the water. So we get this plus water. And so the key is that the cation remains dissolved in the water. Releases cation, which stays, how can I say this? Dissolved, okay, I'll just use the word dissolved. Stays dissolved in water. So calcite does the same thing. This is how caves work. You get calcite plus water. We get a reaction where the calcite breaks down and releases cation, calcium 2 plus CO2 plus H2O. And we could put something like example caves. What does this look like in a picture form? I like this one quite a bit, right? It's just a statue made of a limestone. We can see the sculptor did not sculpt this terrifying baby without a nose, but over 200 years of rain falling across this this statue, it's lost some of its features. Those features, you never saw granules wash away because it all happened in a chemical dissolution state. So there is our dissolution. Now later, this stuff can reprecipitate. That's how caves work. That's how salt deposits form. But right now, we're not building rocks, right? We're destroying them. So we're worried about dissolution. All right, the second chemical reaction I would like you to know is called hydrolysis. Hydrolysis. And it's a cousin to dissolution where, in fact, some textbooks group them together. I would like to separate them here. Hydrolysis, we have attack of water again. So, but it's an attack where there's a replacement that goes on. So I'd like you to say water replaces cation in a mineral. The cation goes away and OH sits in its place. So maybe I haven't said this right. H2O replaces cation in a mineral with OH minus. So what is this going to look like? Oh boy. I did not necessarily write out a great example here, but this is how clays work. And all clays are produced when you take a feldspar. So let's do this. So this is a clay formation, occurs by hydrolysis, and we take something that's called a feldspar. Feldspar is a group of minerals, plagioclase, microcline. These are very important rocks. It's the pink in granite. It's the white in granite. It's the feldspar is like the #1 mineral in the Earth's crust, actually. And if you add water to that feldspar, you produce a clay. And the clay is a mineral that has OH in its crystal lattice. Okay, didn't do a chemical reaction, that's okay. The key here is that we replace the cation with an OH, and the cation just kind of goes away, it floats away. So let's see, what maybe would be a picture of this process, the picture of clay formation. We can imagine that this guy is standing on a deposit that here is very rich in this orangey clay and this white clay. It used to be granite. The granite had a lot of feldspar in it, but water in a hot climate destroyed that feldspar and turned it into these clays. Okay, that's the chemical reaction of hydrolysis. And then our third reaction is oxidation. This one you've heard of before because oxidation means rust. Oxidation, this is rusting. And in this class, we're going to basically always have it deal with iron. It's not always the case. A metal, in fact, let's go. A metal reacts with oxygen. and it's going to change the actual mineral because it's changing the bonding. So rusting is where you take iron plus oxygen and you get something like FeO, and you're changing the oxidation state. If we're getting more into the chemistry of what's going on here, this is going to produce minerals that tend to be red, brown, and yellow when we're specifically dealing with iron. These often also are just making a veneer. Just like if you have a hammer and you leave it out in the rain, you get a rust covering that metal, but that rust doesn't go all the way through it. It's just this thin veneer on the surface. Let me show you a picture of a rusted rock, and you'll see that maybe this is something you've recognized before. I like this picture in particular. This is the nice part of the rock where the reaction has not occurred very much, but there's a thin rind on the margin here, and that is our oxidation. And this is weaker. It has been altered. It's more readily able to break down. Same thing is being shown here. Here's our core of the rock that has not yet been altered, and here on the outside we have our rind. All right, those are our types of chemical weathering. Next, let's get into mechanical.